Hi, everybody. Why don't we get started? Can everybody hear me? Yes?
Yeah, we can hear you.
Great, thanks. A couple of announcements before we start. The first homework is due today. Hopefully, you'll find it possible to submit it via as a PDF file via Canvas. If you have any trouble with that, send me an email or let me know what the story is, but hopefully that will work out fine. I will have Zoom office hours today at 4:30. If that time doesn't work for you and you want to meet with me, just send me an email. Tomorrow morning at 9:30, so that's an hour earlier than now, we'll have our first Thursday hour exam. So every Thursday at 9:30, there'll be an exam. This one is just for practice. It will be on the topics of two-dimensional one and two-dimensional kinematics, but the problems won't be graded or they won't count. You'll just go through the exercise, and I will tell you whether or not I found that the process worked for you, and you will tell me if the process worked for you. And hopefully any snags or snafus will work out. I'm going to contact everybody but an email early this afternoon with the details about that. But in a nutshell, what we'll do is we'll send you a PDF early before the exam starts that has a password. I'll start the Zoom session early so that everybody's sitting down and ready to go. And then we'll ask you to I'll send you the password so that you can unlock and print the document early if you want. And then the exam will last about 45 or 50 minutes. And I'll figure out the exact timing once I've got everything settled. And then you'll have a little bit of time to scan and get your exams back to me before we start the active session again tomorrow at 10:30. So that's what I'm going to try to do, and we're going to see if it works for you, and if it works for me, and any kinks and bugs. You don't have to stress about it because we're going to iron them out. We'll have time. Yes, and I will post, so by the way, once the homeworks are collected, I will post solutions to the homework. Those should appear sometime in the early evening tonight. So you get a chance to look at that if you want and see what they look like. I think that's all of the exam important things. Don't forget, there's no class on Friday, Saturday, or Sunday, but I will set up Zoom office hours on each of those days for students who have questions. Anything that anybody wants to check with me about regarding the course at this point? All right. So our focus today is going to be on the topic of Newton's laws. So we're changing gears from kinematics to dynamics, which I kind of explained in the asynchronous video earlier. And we did one example of a block in an elevator. So I want to do a few more examples, and the idea of what we're going to do today is to demonstrate repeatedly a particular recipe for tackling the class of problems that I call Newton's laws problems. And there's a recipe that I like to get everybody into using. And one component of the recipe is the application of the force menu. So I haven't included the whole list of them, but I emphasize here that if you're going to infer the existence of a force, you have to infer the existence of one of these four forces corresponding to weight, normal, tension, which we haven't really talked about too much, and friction, which we'll talk about a little bit more today. In fact, I want to start with friction because friction can be a topic that students find both befuddling and yet at the same time oddly intuitive or counterintuitive. So let's start with a simple example. So this will be example 1. And so I'm going to set up the problem this way. I'm going to put a block on a table. So this is a table surface. And I'm going to have the block sitting on the table. And so I'm going to give, what are the givens here? So the given here is the mass of the block. And then I'm going to come along with my finger or some other device, and I'm going to apply a force to the side of the block. Okay, so I'm going to label this force F app. And that will be my usual trick for an applied force. So if I give you a force, I will often tell you that the force is an applied force. What I mean by an applied force is a force that you don't have to infer that it's been given to you explicitly. So, for example, I might come along and apply a force of 10 newtons or something like that, and I might tell you that in the problem. So I'm going to put this it's not really on the force menu, but it's kind of down here in the corner, literally down here in the corner. These four forces are forces that you would infer their existence from, where the applied force is a force that I would give you, or that would be given to you on a problem. Okay, so these correspond to the forces that, all of these correspond to the forces that you might consider putting on your free body diagram, but you must not put an applied force on your free body diagram unless it's actually been given to you in the statement of the problem. Okay, so here's a free body diagram. Here's the problem. Given M, given what else is given? I'm gonna make sure we get all the givens here. Given F app, so that's also the magnitude of that force in this direction is basically given. What are we gonna do? Find all the forces. This is the actual usual generic form of stating the problem. Is that you set up the situation. You've got a set of givens, and you're asked to infer one or more things, and typically those things are the values and the types of all unknown forces that correspond to the particular problem. So what does the recipe say? The recipe says, take the problem, however it's stated. The first step is to draw a diagram and make a list of all the givens. Well, I kind of did that for you. So yeah, that's step one. We're in good shape. Step two, and this is important. It's important because it helps you keep track of what you know and what you don't know for the whole problem. The tricky thing about using symbolic solutions is that not all symbols are the same. The symbol M and the symbol F app correspond to givens, whereas the other symbols will correspond to things that we have to calculate. So we're always trying to figure out what we need to know, the forces, in terms of what we're given. Okay, so one of the things that we want to infer right off the back is what can we say about the acceleration? So in this case, I've got a force applied to a block on a table, and then another given, this is the final given, is that the block stays put. Okay, so let me demonstrate that. It's easy to demonstrate. I've got an eraser here. Fell down, let me try again. Got an eraser here. It's sitting on the edge of this chalkboard, but it's like a table. Take my camera down just a touch. Okay. I'm sitting here and I come along and I apply force. And as a result of applying the force, it doesn't move. It stays put. So there's some force I'm applying. It's a given force. And then I observe that the block stays put. So the way to think of this is, let me put this back to roughly there. So the way to think of this is that these things are basically given parameters, but this thing here, the block stays put. What I'm telling you, this thing is called a kinematic constraint. Kinematic constraint. In other words, it's a statement about the observed motion of the bodies in the problem. So in this problem, we observe that the body stays put, so it stays at rest. So that means that what we can say, given this kinematic constraint, what we can say is that the acceleration in all directions is equal to 0. So that's worth keeping in mind, because once I know this, I want to keep that. I don't want to forget this for the rest of the problem. If I know the acceleration and I know it's 0, I can take advantage of that anywhere else in the whole problem. So again, I always start with this step 2, check the acceleration. because if you forget what's going on with the acceleration and you just start doing algebra, you'll make an awful lot of needless work for yourself if you don't keep track of what you're doing. Okay, so what do we do next? So step 3 is the free body diagram, FBD. So what do we do with the free body diagram? Well, first, a couple of things. The first thing I do is, if you've taken a high school physics class, for every different class you take, every instructor will give you a different set of rules about how to draw a free body diagram. Sometimes they will have you draw the free body diagram on top of the sketch. Sometimes they will have you label the forces in very particular ways. For my purposes, the free body diagram serves a critical, the critical issue is, what is the nature of the word free here? So to get at this, so what do? So all of my free body diagrams, and again, I don't insist, but I encourage you to switch from whatever mode you've done in the past to the mode that we're doing in this class, being flexible and changing the way you solve problems as part of being in a college class, right? So I just draw a box to make it clear that I've got a free body diagram. So I usually label at the top free body diagram of whatever it is that's coming into play. So this, in case, it's the free body diagram of the block. And then I don't bother to draw the details of the figure because I'm treating the body as a point-like object. So I just treat the body as a point. So all of my free body diagrams basically look like a box with a point. And all I'm doing with the free body diagram is I'm using the free body diagram as a bookkeeping device for keeping track of what forces are on the block, or what forces are on the body. Now, here's the key thing. What's the free part, right? Because what do I mean by free? I don't mean it costs you nothing. And obviously, the block is not free in the sense that the block is being affected by forces, and so it's not free in the free and open and out in space sense of the word. The word free here means applied. It means consider the forces on that block free from any other considerations about what anything else is happening anywhere around. Now you may say, Mr. Cobalt, the only thing that's happening is you've got a block in this problem. That's true. In this problem, I've only got one block. But I could imagine, and we'll get to problems where I've got 2 blocks, 5 blocks. I could have different forces. I could have interactions between systems and pulleys and all kinds of complicated things going on. And the idea of the free body diagram is I ignore all the details of every force on every body except for those particular forces that are on the particular object here. Okay? So in this case, I've got a block. And I want to draw the forces that are on the block. So how do I do that? So what I do is I go to my force menu, and these are the forces that I can infer, and then this is the force that I can use if it's given. So in this case, let's start with that given force because it's a given force, and I know it's being applied to the block, so I'll just draw it, okay? And I don't care how long the arrow is. The purpose of the free body diagram is not to infer the strength, it's to basically keep track of directions and names. And so I will label that force F sub app. All right, so that's just a way of me keeping track of the fact that there's a force being applied on this body in the rightward direction. What are the other forces on the body? Well, I go through the force menu and I ask myself, are any of these forces relevant to this problem? And the first force on the top is the force of weight. And what I will say is that as long as the body is in the vicinity of the surface of the Earth and it has mass, which it does, then it must have weight. So there's a weight force, and I will label that force W, pointing downward like that. Okay? And by the way, the weight force is always pointing downward. And this is really important. Oh, hold on. No, not now. Another thing that's important is every body has only, I'll say this twice, every body has only one weight force, and exactly one weight force. And its magnitude is known. It's always mg. So the great thing about the weight force is you just put it down on the body. It's going to be there. Unless I'm in space or something weird is going on, or I tell you to ignore the weight force, you should put it on your free body diagram, and it should be pointing downward towards the center of the Earth. Okay, so these are the two forces that we know have to be there. What about the other forces? So the normal force. So the normal force is a push, and it results from, this is the key idea, it's a contact force. Every force, bing, 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 except for the wave force, is a contact force. And every force, therefore, results from something being in contact with the body I'm in question. If there's a body and it's not in contact with my body, it doesn't belong here. The only way I can get the force on it is if I'm in contact. So in this case, I am in contact with the table. Oh, there I am. I'm in contact with the table. So I'm going to highlight that contact region in pink there. And as a result of being in contact with a surface, it is plausible that there's a normal force. And the normal force always points away from the surface of contact towards the body. In other words, it points from the surface in towards the object. In other words, I'm the block. The block has to have, would experience a push up. Now the table experiences a push down, but I'm free body. I ignore the table. I only focus on the block. The block experiences a force, normal, which is to say perpendicular to the surface, and it's a push. So it's got to be a push upward. Now you may ask, how do I know that force has to be there? And the answer is, you remind yourself, the acceleration of the block is 0. Therefore, it must be true that the net force, F net, by Newton's second law, is also equal to 0. In other words, Newton's second law comes in even when I'm thinking about the free body diagram and asking the question, does the force belong there? There has to be a force in the upward direction. Otherwise, this body will fall down. And we know it's not falling down. You can see it. It's sitting right there. So there must be another force that's pointing upward. And that force has to be a push. And the only force on this menu that could give you that push is a force upward. So I'm going to draw that force upward, and I'm going to label it N, like that. Okay? So that's my normal force. And then finally, I keep going through the menu. I say, okay, what about the tension? There's no strings. There's a string or a rope or something like that that's manifestly pulling, and there's nothing going on here. So that's no. And then finally, friction. And you might say to yourself, well, should there be a friction force? What is a friction force? So here's the key thing. The definition of friction force is a force parallel to a surface. That is the definition of friction. That's all the definition we need for now, is any force perpendicular to friction. Yes, there's two types of friction. There's static friction and sliding friction, but we're going to, for the rest of the week and until next Monday, we're going to ignore sliding friction. We're just going to look at examples of static friction. And the key idea is, just like the normal force, the static friction force, we don't know, unless it's sliding and slipping where you have a special case where you can use a special rule, you generally speaking don't know either the magnitude or the direction of the friction force. But if I look and I say, which way does the friction force point? Well, I know that if I'm applying a force of this way, there must be another force, some other force that's being applied this way. And the reason I know that's true is because, again, the net force on the body is equal to 0. So again, even while you're putting together your free body diagram, consider the acceleration and consider what it tells you about the net force. It has to be the case that all these forces add up to be 0. So if I've got a force going this way, there must be at least one other force going this way. And since I've already used up the normal for being perpendicular, I have to have a force that's parallel to the surface of the table. So by definition, that force is a friction. In other words, any force that arises due to that being that contact that's parallel to the surface, that has to be friction. So that's my free body diagram, except for I'm almost done, except for I want to do one last thing. And again, I guess I would call this voluntary mandatory, which is to say, if you don't do this and you screw everything up afterwards, I don't know for sure that you've got this idea right. Now, you may have learned this in your high school. You may have not learned this in your high school. But in order for me to make accurate use of this bookkeeping device, I need a coordinate system on my free body diagram. And of course, I've somewhat crammed that free body diagram into the corner. So I'll put my coordinate system. Usually I tuck it into the corner right here, but I will draw it nice and big so you can see it. I need a coordinate system so that I can actually work Newton's law. So I'm going to use, in this case, a standard coordinate system with x pointing to the right and y pointing to the left. So the components of the free body diagram are a name so that I know which body I'm talking about, a point, arrows and labels for all of the individual forces appropriately labeled, and a coordinate system. All of those things have to be there. And by the way, if you don't have this free body diagram right, you try to use it for the rest of the problem, it won't work. The most important step of everything is to make sure you got the free body diagram right so that you can then proceed to solve the problem correctly. Okay? All right, any questions about the free body diagram? Just want to make sure, because this is really important. And there's no other forces. We've already got the force, the applied force. And as a result, and by the way, there's only the way I know there's no other forces is that this is the only surface that's in contact with the body. And this force here, well, that's also in contact, but it's in contact there. So what I do, I kind of make, to ask myself, are there any forces? I sort of follow the perimeter of the object, kind of like an ant crawling around. And I ask, where are the contact points? And those are where the forces could come in. On this surface, I could get both normal and friction applied. Questions? Anything? Okay. So let's start that. Finally, let's just go to the final step of the problem, which is to apply Newton's laws, one body, one coordinate at a time. So this step requires me to apply we're going to apply Newton's second law. So what I do is I say, okay, I got to remember, you have to explain your work. So the free body diagram is sort of self-explanatory. I've already explained the acceleration, but now if I'm going to apply Newton's laws, I have to write down what I'm actually doing. So I will write down, what I'll write down is the name of the law, Newton's second law, which I'm perfectly happy to have you abbreviate simply Newton's second law, or NSL, whatever you want to do. And then I need to label the body. So Newton's second law on the block, and I have to apply the body law, one body, one coordinate at a time. So I'll start with the vertical coordinate. Okay, so y coordinate. Okay, so what I do is I stare at the free body. This is so important. Let me make a point real quick. If you get this recipe and you can apply it reliably to problems of increasing sophistication, you can't fail this class. This is the most important thing for the whole class, is the application of Newton's second law. There's nothing more important. Everything else in terms of the core of the course is gravy. I will find every opportunity I can to ask you, can you show me that you can do Newton's second law problems? So this is the most important thing. So I start with, so what I do is what is Newton's second law? Newton's second law is F equals ma, but again, it's the net force, right? So what I do is I write down F. So if I'm going to apply the second law, this is so important. If I'm going to apply the second law, I'd better start by writing down F equals ma. If I skip this next step, and then you mess up. If you skip this step where you don't write down F equals ma, you just write down something else, and it turns out that something else is wrong, I can't give you the partial credit that I would have given you if you'd simply written down F equals ma and started from there. But F equals ma is not enough. I need to make it clear that this is the net force. And more importantly, I need to make it clear that this is the net force in the coordinate that I'm interested in. So in other words, I'm obligated to label this object the net force on the block in the y direction. So in other words, there's only one body here, so I'm just going to call this F sub y. So when I write down F sub y, this is really important. When I write down F sub y, what this thing means is the net force. I mean, I could have put the word net in there, but I don't, that's an extra step. The net force in the y direction. So F sub y means the net force in the y direction. Notice that there's no vector hat on top of this. So this basically corresponds to the component of the force in the y direction. You see what I'm saying? This is a number, not a vector. There's no arrows on here, right? And then, of course, now this is the acceleration in the y direction. And this is the mass of the block, right? So then I've got that step written down. So the next step is I actually put in the things that I know. Well, in this case, on the right, so in other words, I have to consider the left hand and the right hand side separately. On the right hand side, I ask, what is the acceleration of the block? Lo, there is the block. Its acceleration is 0, and therefore that is 0. So on the right hand side, I get that this is equal to 0. And on the left hand side, what's my technique? My technique is I stare at the free body diagram. I take all the forces that are pointing in the positive y direction. So that's why I've got this coordinate system here to remind myself. All the positively pointed forces add, the components add, and all the negatively pointed forces subtract. So in other words, the thing that belongs on the left-hand side is the normal force minus the weight force. Okay? Notice, look, Mom, no arrows. No arrows on top of N and W. The reason that there's no arrows on top of N and W is because these are not forces. These are the magnitude of the normal force and the magnitude of the weight force, which is things that we're trying to sort out. So this is not a vector equation. This is a one-dimensional kinematics equation. I broke in the forces into the individual components, and now I'm going to actually work out what those are. Okay? So then we consider now, once we've written this down, we say, oh, well, I know what the weight force is. That's a given. The weight force is a known force, so that's equal to, well, in this case, I'm labeling it that's big M. So I guess I should have made this big M. Big M times G, so that's equal to 0. And then I finally get that the normal force is equal to big M times G. And I stop there because I go, oh, that tells me the magnitude of the normal force. I now have an unknown, which is the magnitude of the normal force. So now I find all forces, right? So I found the weight force. Yay, there it is right there. And I found the normal force. Yay, it is right there. And by the way, this step where you figure out that the normal force is equal to mg for problems where there's no acceleration on the body in the vertical direction, this will happen. You'll do this 30 times. But nonetheless, there it is. That's the answer. Okay? That's the horizontal forces. What about the vertical forces? So I'm just going to erase up top here. So let's see the answer without totally erasing everything I've done so far. I'll leave the acceleration there again. So next step, Newton's second law, apply to the block. For now, the x coordinate. So I always start with the Newton's second law. F equals m, which in this case is big M, times a. And again, now I'm working in the x direction. So that's F sub x. And F. So this thing is the net force in the x direction. And this thing here is the acceleration in the x direction. But we know the acceleration is 0. So that goes to 0. So the rule that you don't plug in numbers has an exception. Anytime you can plug in 0, whoops, one person waiting. There we go. Anytime you can plug in 0, you're allowed to plug it in. Okay? All right, good. Just make sure nobody else is waiting to get into the room. All right, good. So let's see. So we carry on from there. So again, the right-hand side is now equal to 0. And the left-hand side, again, we stare at the free body diagram. And we say now we're working in the x coordinates. So forces that pointed to the right add, and forces that are pointed to the left subtract. So I say that the applied force, F sub app, that's adding, minus the friction force, is equal to 0. And I know that the friction force is, the applied force is known, so that's all set. So that's a given force. So I'll just kind of put a little box on that. But I don't know the friction force. So I solve for the friction force. The friction force is, well, I just bring that over here and then swap. I like to have the unknown in terms of the knowns. So the friction force is equal to F. Yay. I put a box on it. Why have I put a box on it? So I now have all 4 forces, 1, 2, the weight, the normal force, the applied force, and the friction force, all expressed as either givens or in terms of givens. In other words, everything is basically expressed in terms of the knowns. Every unknown is now expressed in terms of an unknown. And I've explicitly indicated the directions of the forces. So now I basically described all 4 forces in this problem. I know everything about every force. That's the recipe. Any questions about that before I go to another problem? Okay. Going once, going twice. Again, I will write this. This is all written out on a piece of paper that I will scan, and you can study this afternoon if you'd like. Every problem I work in these active sessions, I turn into a practice problem. Okay, let's do another problem. This is a little more complicated. I've got a truck. So I've pardoned my artistic skills where I draw a truck like this, and the truck has a flatbed. So that's the flatbed like that. And on the flatbed is a box of mass M. And so there's the truck, the room, and the truck is accelerating forward with an acceleration given by A. So the truck is going off it goes. Okay, and the box sits in the flatbed, and it does not slip, no slide. So the box is in the flatbed, and even though the truck is accelerating, the box is just staying put in the flatbed, right? So it's kind of the, if this is the box and this is the truck and the box accelerate together. Whoop, they stay stuck together. Okay. So all of this is the setup of the problem, and I basically want to find the force of friction. Well, I just want to find the forces. Let's just find all the forces the same way we did before. Okay. So let's make sure we've got a diagram, but let's make sure we're clear about what the givens are. So in this case, the givens, what are the givens? The givens are the mass of the mass of the block M, and the other thing that's given is the magnitude of the acceleration of the truck A. And then finally, no slip, no slide. That means that the block is stuck to the truck. It moves the same way as the truck does. So again, this is a kinematic constraint. This is a kinematic constraint. No slipping, no sliding tells you something about the motion. This is also, in some sense, the word a kinematic constraint. It tells you how the thing moves. But the fact that the truck is moving with A tells you that the block itself is also moving with A. So in other words, I've got these givens, but I also know the acceleration. Now I want to be a little careful with the acceleration here, because I've got two components of the acceleration. The block is moving sideways with the truck, so I know that the acceleration of the block, and I will make it clear here, A sub B in the X direction, that means the acceleration of the block in the X direction, that is equal to A. We know that. But the acceleration of the block in the Y direction, do we know that? How is the block accelerating in this component? It's not, right? Because even though the block is moving from right to left, it's not going up and down, at least not as long as I don't hit a bump or a hill. So this is equal to 0. So I know what the acceleration is. So again, this is a problem where the acceleration is given, and I want to keep track of the fact that I know what it is in each of these two components. Okay? So now I've done a diagram, I've got the givens, and I've got the acceleration. The next step of the recipe is to do a free body diagram. So I will make a giant free body diagram this time to make it really clear and easy to see what we're going to do. All right, so the free body diagram looks like this. Here we are, there's a free body diagram. There's the, well, okay. So first of all, find the forces, find the forces on the block. Now, you have to be very clear about what you're going to solve for. In this problem, there are forces on the block, but there's also forces on the truck. And the forces on the truck, well, they look complicated because there's wheels that are spinning, and there's an engine. There's all kinds of complication here. But I'm not going to ask you. I'm not asking for the forces on the block, on the truck. I'm only asking you for the forces on the block. So that means I only need a free body diagram for the block. In other words, I don't bother with the truck because I'm only concerned with the block. And I just ask myself, what are the forces on the block? So what's the method? I start with, I've got the free body diagram. I start by going through the list. So I know I've got, so first of all, do I have an applied force on the block? Is there an applied force on the block? Anybody? Yes? No? Do I need to worry about this applied force? I mean, there must be some force on the block because it's accelerating. Is that an applied force?
No.
No, maybe not. So here's the thing. So here's the key. Only use this thing if I give it to you in the statement of the problem. So applied force is my name for a force that I've given you in the problem. If I told you the value of any force here? I've not. So you can't use this. Not for this problem. So no applied forces. That's out. So let's just start. So that means we have to infer every force on the block. It's one of, and all the possibilities are one of these forces because we're limited by the force manual. So I always start with the weight. Why not? The weight's easy. That's the weight. Okay. And because I've got a truck here, I'm going to use a notation to just keep track of what I mean. I'm going to call this the weight force on the block, W sub B. So in other words, you don't need it specifically for this force, but once we have more than one body, you really do need to label each force in a clear and unambiguous way, especially if there's more than one of each type of force. So for starters, I'm just going to label that the weight force. I'll make that a sharp, pointy W. The weight force on the block. That's how I'll label it. And since the truck is not accelerating downward, the truck isn't falling into the ground, and it's not accelerating upward, there must be a balance. Again, the second law tells you that the net force in the y direction is balanced. So that implies that there must be a normal force as well on the truck. So I'll label this N sub B. Again, that label B is not strictly necessary here, but it's a habit I'm going to start putting in so I keep track of which forces are on which blocks, which bodies. So when I say force and a subscript, that means the force on that subscript. One subscript means this is the weight force on block B. This is the normal force on block B, which I'm calling, that. And then, so what's next? So the next thing is, what about the horizontal forces? Are there any, by the way, there's no tension, there's no strings. What about friction? Is there friction in this problem? What do you think?
Yes.
Yeah. And by the way, the tricky part is here's the thing. Suppose one way to think of is there friction on the block is to ask yourself, what would happen if there's no friction, right? So in this problem, if I coated the flatbed of the truck with a layer of glare ice so that I basically turned off friction and the truck was accelerating this way, what would happen to the block?
The block would slide off.
The block would slide off. So there must be friction. So that's good. So there's friction. And I know that the friction has to be parallel to the surface. So again, here's the surface of interaction right here. So the only choices for the friction force are to the right or to the left. So in this problem, now by the way, in this problem, which way is the force friction? Is it to the right or is it to the left? That's the tricky part. How are we going to figure it out? Now, you may have learned a rule in high school. And this is the rule that you may have learned in high school. The friction acts in opposition to the motion. Anybody heard that rule before? Is that a rule you've heard before, maybe? Okay. It's not true. It's not a good rule. It's not helpful. It's a lie. It's a myth. If you learned it, you either the person who taught it to you was mistaken, or they taught it to you in a way that you learned it without understanding the subtleties of the issue. So it turns out the way to figure out where the friction is that it acts in opposition to the motion is not a good rule. And in this problem, it's easy to demonstrate why that's true. How do I know which way the friction points? The only way I can figure out which way the friction points is to apply what's my favorite law of physics? My favorite law of physics is Newton's second law.
Second.
Yes, F equals ma. So I look and I say, what do I know about the acceleration? I know the acceleration on the block is equal to a. That means that the block has to be accelerating to the right. And there's no other force on my menu that could possibly give me a force to the right except for the force of friction, because every other force either isn't there or applies perpendicular and not parallel to the surface. So that means that the only option I have is that the force of friction must be applied this way. And again, I'm going to label that F sub B for the force of friction on the block. Okay? In this problem, what is the direction of motion of the block? To the right. What is the direction of friction on the block? To the right. This problem is manifestly contradicts any rule that you learned in high school that the force of friction opposes the motion. In fact, quite the opposite. In this case, the force of friction is in the direction of the motion. It is the cause of the motion of the block, not the obstruction of the motion. Okay? Any other forces? No, because I've gone through the whole menu and that's it. By the way, you can't have two friction forces on the same surface. There's only one friction force allowed per surface of contact, one normal force per surface of contact. So that's it. And the only other thing I need to include in my free body diagram, as before, are these coordinates X and Y. Okay? Those are the only forces on the block. So now that we've done that, let's work out the quantities that we want to do. So again, we start with Newton's second law. And I usually, in these problems, I usually like to start with the Y coordinate because it's sort of the same thing every time. So again, I write down the net force on body, which I've labeled B, in the Y direction is equal to the mass, which in this case is given by capital M, of body B, M, times the acceleration of body B in the Y direction. So you see, this is how I write down Newton's second law. Every time I write down Newton's second law, I put these subscripts down to keep track of which body and which coordinate I happen to be applied to. So this is Newton's second law on body B in the Y coordinate. And again, no arrows here. Okay, these are core components, the magnitudes of components, not that. But in this case, I know what a sub by is. Oh, it's 0. So that makes this thing easy. And then again, I get on the left-hand side, I get the usual thing. I get that the normal, again, I look at this normal force pointing up. So that's N sub B minus the wave force pointing down, which is W sub B is equal to 0. But W sub B is equal to mg. So I just write that down. W sub B is equal to big M times G. And N sub B is equal to, well, I'll skip the algebra because I'll bring this over here and set that equal to mg. So I can show right away that N sub B is also equal to mg. So in other words, these two forces have the same magnitude, but they're oppositely pointed. That's a result that you will find quite frequently. Now we do the same thing for Newton's second law in the X coordinate. Okay, so again, the same body. So I start with F equals ma. So F equals ma, but this would be capital Ma. And this is the force on body B in the X direction, and this is the acceleration on body B in the X direction. But the happy news is I know, again, I always deal with one side and the other separately. I don't start doing algebra. I stay away from moving across this equal sign until I've completely dealt with each side. So I now know, oh, a sub bx, that's known. So the right-hand side is capital M times capital A. And the left-hand side is, well, I look at the free body diagram. This is so important. You can't just write something in here. You have to look at the free body diagram, look at the coordinate system, and say, oh, what are all the forces in the X direction? Oh, there's only one, and it's F sub B. So F sub B, that's the only one. Oh, I'm done. Okay? So now I know the values, the magnitudes, and the directions of every force. Notice that the answer here doesn't depend on the coefficient of anything. The only way to calculate the unknown friction force is to apply Newton's second law. If I had, suppose at the beginning of this problem, I had given, suppose hypothetically I was Professor Evil and I had given you some coefficient of static friction. How would that have changed the answer here? What I'm saying is it wouldn't have. That's a useless thing. It's, in general, the coefficient of static friction, it doesn't help you calculate the value of anything. At least not in particular. It doesn't help you calculate the value of the friction. Now you might say, well, Mr. Caldwell, the static, yeah, it turns out it's static friction because there's no slip and no slide. But that detail, I'm not going to worry about for now. For now, I'm going to treat the force of friction just like normal, just like tension. It's an unknown force, and the only way to find it is to use this. And that's the habit you want to be in. Any questions about this? See the method? Write it down, put down the givens. So important. Before you start, make a note about the acceleration because you're going to want to use that. Then write down the free body diagram, go through the force menu, figure out what belongs there and which way it goes. Remember, the force of friction only applies the direction of the force of friction. How can I tell the direction of the force of friction? The only way you can absolutely guarantee the direction of force of friction is by applying Newton's second law and figuring out, oh, there has to be, in this case, there has to be some force in the positive direction. And then once you've done it, apply the second law in detail, F, net force, and then the other side, and so forth and so on. Okay, any questions? Okay, do I have time for one more example? Yes, I do. Okay. Okay, so this is an elevator. And in this elevator, I've got two blocks. The lower block, I'll color in pink, and I'll label this block B, and an upper block here, which I will label A. So what are the givens? The givens are the masses of the two blocks, so that's MA and MB. And then I'm going to say that the elevator as a whole is accelerating upwards, like this, with some given acceleration, which I will call A sub naught. So A sub naught is the acceleration of the whole elevator. Okay? And what I want to do is I want to find all the forces on both blocks. Okay? So again, steps. I've got the diagram, I've got a list of givens. I know what the problem is. What do I know about the acceleration? So I've got the acceleration. Let's start with the acceleration of block. Let's start with the acceleration of block B. What can I say about that? Well, see, it's the block B is sitting on the floor of the elevator, and the elevator is moving at A naught, then B and A are stuck together. In other words, anytime two bodies are stuck together, they must have the same acceleration. So it must be true that the acceleration of block B in the y direction is equal to A sub naught. But block A is also stuck to block B. I mean, in this problem, block A doesn't go flying off. Block A and block B are stuck together, and both of them are stuck to the elevator. So again, that's the same thing as A sub AY. So again, when I write down A sub BY and A sub AY, I mean A, the acceleration of block B in the y direction, and this is the A, the acceleration of block A in the y direction. So again, this is a kinematic constraint. I write that word down again, kinematic constraint. It has nothing to do with the forces that are coming into play. It has to do with how the problem is set up and how the motion is being observed. I'm observing the motion of these two blocks. I'm observing, now if I'm standing outside the elevator, I notice that each block is also accelerating upward with the same acceleration A naught. You know that because they're stuck together. That's the constraint. Okay? So now we got two bodies. So I'm going to have to do two free body diagrams because I want to know all the forces on all the bodies. So the most important part of this is to do the free body diagram. So I will do, I've got enough room up here to do two free body diagrams. So this is free body diagram A, and this is free body diagram on B. And again, I label each object with a point. And the question is, which free body diagram do I start in? The answer is, it doesn't matter. But as a rule, I like to start with the free body diagram when things are the simplest. Now, start with the simple one and then work from there. So in this case, it's simpler. What's going on with A is simpler than what's going on with B, because A is only in contact with B, whereas B is in contact with both A and the floor of the elevator. So let's start with A. So what are the forces on A? So there must be a weight force on A. So I'll label that W sub A. And the happy news is I know what W sub A is. It's just MAG, right? M sub AG. So that's fine. So we got that force there. Any other forces on A? Well, A is in contact. So again, I asked myself, where is A in contact? A is in contact. The point of contact is this surface. And in this case, A is not moving sideways at all. So there's no sideways forces. So I'm not going to worry about this, and I'm not going to worry. There's no applied forces. I mean, there's tension. So the only other possibility is a normal force. And so that's the normal force here. And applied this. And this is the normal force. So let's get the label on this just exactly right. Let me rewrite this a little bit better so you can see it. So this is the normal force. Label this in green. This is the normal force that's applied to block A, but this is the important step here. The normal force applied to block A, but it's due to being in contact with block B. So this is not the only normal force in the problem. There's a lot of other normal forces, and in this case, this is the normal force on block A due to block B. So again, AB. So again, there's this basic idea. If I write down N sub AB, this means the force on A due to B. That's my notation. If I say AB, that always means a force on A due to B. That means that all the forces in free body diagram A had better, if they've got two indices, the first indice had better be an A. Any other forces on this body? No, because there's no horizontal forces and we've done all the vertical forces. Coordinate system, I'm just going to label the coordinate system upward Y as my coordinate because there's no, I don't need X. I'm just going to use Y. You just put down the coordinates you need. All right, so now let's do the free body, let's do the forces on block B. So we do the same kind of thing. There's a weight force on W sub B like that. Yes? By the way, is there a weight force on block B due to the weight of A? Anybody?
Yes.
Now you might think so, but again, the rule is that all, so even if your intuition says, I mean, how can I put it? When I had toddlers, yes, I'd be lying on the living room floor and one of them would jump in the air and land on me. Ah, hi, Dad. Okay. And I would say, in English, I would say, oh, I feel your weight. But in fact, I don't feel the toddler's weight. What I feel is the toddler coming in contact with me, and the strength of that contact depended due to these laws on that toddler's weight. But I know directly, until the toddler is actually in contact with me, that weight force isn't relevant. And in fact, everybody only feels its own weight. So the rule is always only one weight force per body. So really it's just W sub B and that's it. There's no WA on this. But what about the surfaces? Well, there's two surfaces of contact, one of which is this one here, and the other is this one here. So in other words, the block is in contact with the floor, and so the floors must be pushing on the block. So let's put the floor pushing on the block here. So this is a force. This is a force normal, and it's the force on block B, N sub B. But now on B due to the floor of the elevator. So I'll call that N sub BE to make it clear. That's the normal force on the block due to the elevator, and it points up. But that's not the only point of contact. The other point of contact is this surface right here between B and A. And here, A is basically pushing down on B. B pushes up on A, but A pushes down on B. So there must be another force. And so I've got to make room. So what usually my trick for making room is to make the dot just a little fatter for another force. And again, it doesn't matter how long the area is, it's just what direction it is. So this is also a normal force. So this is a normal force. And then what kind of force is it? This is the force on B, but now due to A. So this is N sub BA. Okay? So this is not a weight force, it's a normal force. It's a A is pushing down on B, so it must be a push. N is a normal force, it's a push, okay? And again, I've got a coordinate system, which I'm gonna sneak in right there. And now I've got all the forces I need. So now I can actually do the problem, okay? So let me keep in mind this acceleration business, but I'm gonna erase just enough of this so I can actually work out the answer. So let's start with the simple one. That's this one, A. So I say Newton's second law on block A in the y coordinate. So in other words, I always start off indicating which body and which coordinate I'm working in. And I have to say Newton's second law, okay? So I write Newton's second law, that means I've got to write down F equals ma. So I'm gonna write F equals ma, but I wanna make the labels sensible. So this is the net force on which body? On body A in the y direction, F sub ay. Notice I don't put F net, I put F sub ay. This means the net force on body A in the y direction. Then which mass? It's the mass on body A. And which acceleration? It's the acceleration of body A in the y direction. So I promise you, if you write this down and you don't do any algebra after this point, you just say, oh, forget it, I'm not gonna do it. I'll give you at least a quarter of the points, maybe more, for partial credit, because you've set up the problem correctly. There's nothing more important than getting this and this right. The rest is literally, technically just algebra, right? Well, there's inferring a few other things, but you're mostly there at this point. This is the important part, okay? So now I treat each side separately. I usually deal the right-hand side. So the right-hand side, m sub a, that's a given. So I keep that in my mind. And then a sub ay, we already worked out that a sub ay is equal to another given, which is a naught. So the right-hand side is now expressed in terms of things we know. Ma. So now this is the key idea. You got to keep track of what you know and what you don't know. I know this and I know this. What about the left-hand side? The left-hand side, I use the free body diagram and I write down n sub a b minus, I'm sorry, I scrunched it there. Let me slightly unscrunch it. N sub a b minus the weight of A. No arrows here. Don't put arrows here. Those arrows don't belong. These are all magnitudes. I add the ones going up. I subtract the ones going down. That's equal to this. Well, I know what the weight is. So N sub AB minus M sub AG, that's the weight. That's equal to M sub A sub naught. Yes, with me? And then I solve for, again, I know this, I know this, I know this, I know this. The only thing I don't know is this. So I write down N sub AB is equal to, I bring that over there, and I get, oh, look, that's just a little bit of algebra to write down M sub A times, that would be A naught, and I bring that over there, and that becomes positive, so I get A naught plus G. Oh, there we go. An unknown in terms of the given parameters. I've calculated this. Notice that the normal force is not equal to mg. It's equal to m A times A naught plus G. This, by the way, is exactly the same result that we got for the block sitting all by itself in the elevator before. It's the same problem. It's just I've now worked more carefully with the indices. So far, so good. I'm going to leave that there for a second, and I'm going to do the last thing, and then we'll be done. So that's Newton's second law on body A in the y coordinate. So I now know I know manifestly, I know the weight force, and I know N sub AB. So I just have to, so I figured out all the forces here, and now I just have to work out the forces on block B. I'm going to erase this. Okay, so I'm going to keep checking my answers over here. So W sub A is equal to M sub AG, and N sub AB we worked out is equal to M sub A times A naught plus G. We've got those answers so far. So now I apply Newton's second law on block B, and again in the y coordinate. I don't have to worry about X this time. So again, I write down the same thing, F equals MA This is the force on block B in the y direction. This is the mass B, and this is A on block B in the y direction. So F sub by is equal to m sub B times A sub by. That's the second law. You got to write that down first. If you write anything else down and you skip this step and you screw up, I can't give you partial credit. That's the whole idea. Okay? So we deal with the right-hand side. Oh, this is good. So we know what A sub by is. A sub by is just equal to A naught. That's the kinematic constraint. And then I look at this free body diagram and I add the positive and subtract the negative. So I've got three forces now. So I say N sub BE is equal, I add that, N sub BE is added. Then I subtract W sub B, and then I also have to subtract N sub BA. So I've got that expression. And then, of course, I know what WB is, so let's write that down. N sub BE minus M sub BG minus N sub BA equals M sub A sub naught. And so, by the way, keeping track now, I know that W sub B is equal to M sub BG. We already got that. That's easy. So how do I deal with this equation? Well, I know the masses. I know that acceleration, but I got two normal forces. And in general, I don't know those normal forces, but there's a special thing. This normal force here, this force right here, right here, N sub BA, this normal force here, and this normal force here, N sub AB, are the force that results from the interaction of the two surfaces, one body against the other. So I can use, in this particular case, I can use Newton's third law, which says that any force that's on one body due to the other, so in this case, N sub BA, is oppositely directed, well, I already got that in the free body diagram, and equal in magnitude to the same equivalent force on the other body due to the first body. In other words, if I swap the indices, as long as I've kept with this on-do business, if I swap the indices, I can say N sub BA is equal to N sub AB. That is Newton's third law. Just Newton's third law technically means if you've got two forces labeled properly, swap the indices and they're equal. That's literally what it means. Equal forces on two different bodies. So that means that I've solved this problem because that means that is this. So I know what N sub AB is. So I just plug that in just because I now know it. So then I've got N sub BE minus M sub BG minus, well, I plug this in. So this is all going to be in brackets because I've got to put a minus sign in front of it. So this is equal to M sub A times A sub naught plus G. All of that in brackets is equal to M sub A times A naught. Ooh. So I'm doing good, but I'm running out of room on my chalkboard. So what I'm going to do is I'm going to jump magically to the answer, which I will put in right here at the top.
Can I ask a question before you erase?
Sure. Yeah.
Why is it M sub A on the right side of the equation and not M sub B?
Oh, because I'm a screw up. Thank you. I messed up. So that should be N sub B, and that should be N sub B, and that should be M sub B. Thank you. I made a mistake is the answer. Good. I went from here to here. I went doop, and I made a mistake. Okay. Now we're good. Yes. Thank you for catching that. I will occasionally have a little oops. So now we're in good shape. Yes. Anybody have any questions? Any other questions before I jump to the front? I have to say, technically, all I'm doing now is algebra, and algebra is easy to make mistakes. If you make an algebra mistake, I won't give you all the credit, but I will only, if it's a small algebra mistake, like for example, if you had done what I did, I would have taken away a few points, but I certainly wouldn't have taken away most of the points. It's a small mistake. I mean, it is a mistake, but it's not as bad as, it's small. For example, a big mistake would be forgetting one of these forces on the free body diagram. All right, so just for completeness, let's write the answer. So I bring, let's just do the algebra in my head. So we're out of time. So I bring this term over here. So I get an M sub BG over here, and then I get these M sub A. So the M sub B's, the G's and the A's add up. M sub A's, the G's and the A's add up. So it's pretty easy to convince yourself if you do the algebra. And again, I will have this on the practice problem, that this is equal to the sum of m sub a plus m sub b times the sum of a naught plus g. Okay, so if you've done the algebra right, that's what you will get. It's not that hard to show. Okay, so this is the method. We set up the problem. We work out what the acceleration is. So in this case, we know the acceleration of both bodies is a sub naught. We write a free body diagram, keeping track. Sorry, this should have an arrow over it because that's a normal force. Keeping track of coordinate systems and keeping track of the indices. We're using the on-do system. Remember, only one weight per body. Otherwise, you use the force menu. And then you keep track of the forces as you know. As you figure out the forces, you keep track of the ones you know, and you solve for the unknowns in terms of the knowns. Well, that's your answer. We've got all the forces, all the bodies, we're all set. That's it for today. So I'll stop. But if people have any questions about anything I've done today or any last minute questions about the homework, I'm happy to answer those questions as well. Otherwise, have a good day, and don't forget to turn in the homework by 5 if you can. And I will send a reminder about the Zoom link for office hours at 4:30, and I'll also send out the details about the practice exam sometime this afternoon as well. Thanks, everybody.
Thanks.
Sure. So does anybody have any questions?
Professor?
Sure.
I asked a question about the homework problem 5, about the plot, about the graph.
About the graph? Yeah. This is the problem with the spaceship.
So because the spaceship. So according to the spaceship, it should be like turn at the halfway.
Right.
So I know the purpose kind of like to slow down. So I know like for the position, it should be like always be positive. But the question is about the acceleration. So after it turn over, then depending on the spaceship, the acceleration should be turned to negative. But if we think about like a x-axis, then the acceleration should be never change. So in the graph, how should we draw our acceleration function?
Hi, I'm happy to tackle that question. So this is an example of the kind of problem where the acceleration is not constant for the whole problem, but it's constant in certain intervals, right? So I call this a kind of, it's a kind of compound problem. It's basically dealing with it, but I'm asking you to make a plot for the whole interval. So let's see if we can infer what the answer is. So usually the trick is I'm going to make 3 plots, one with acceleration, one with velocity, and one for position. That's the usual trick for these problems, right? And so, physicists love to plot things, so this is all as a function of time, okay? And let's start with acceleration, and we'll call this 0, and we'll call this essentially halfway there. So I might call that t1/2, and then I'll call this the total time to get to sedna, which I'll call t sub s. You can call them anything you want, just as long as it make it clear that this is the half. It's not exactly half. That's about halfway, right? Okay, right. Are you with me so far, yes? And so we start off, so if that's 0, we start off with an acceleration that's not 0, right? We start off with like this, yes? The acceleration is constant. So a plot of constant acceleration means a flat line as a function of time. Does that make sense? So what happens? So what happens when I get to the halfway point? Now here's the key issue. I have to have an image in my head of the motion. It's kind of a movie, right? So in the movie, I've got 0 to sedna, right? So x sub s. So this is again, this is x in the positive direction. So I've defined this as the positive direction. So that's positive, and that's a halfway point. Okay. So if I'm moving in this direction, and as I go from here to here, I'm speeding up. So my velocity is increasing in the positive direction, and my position is increasing in the positive direction. Everything makes sense, right? But what happens when I get to the halfway point? I have to start slowing down. Right. So how do I represent that in the acceleration?
We should like flip the
Yeah, right, exactly. So in other words, the rate of change of the velocity, now instead of the velocity increasing, the velocity is decreasing. So basically it goes like this.
Okay, I see.
Now, does that make sense? So where this value is positive g and this value is minus g, right? And then it gets back to 0. So that's the acceleration. So in other words, the acceleration is discontinuous. It very quickly flips. The rocket basically goes, and then it turns around and goes, slows down, right?
So we're drawing the graph based on the spaceship.
On the ship as a whole, right? I want to know for the whole ship.
Okay.
Yes, exactly, right. I want to see the whole story. Right, so the whole point of the graph is for you to basically show me that you understand how the movie works, right? So what happens, so now let's go to the next step, right? So let's go to the velocity, right? So again, this is 0, and this is the velocity as a function of time. And that corresponds to 0 time, that's halfway, and that's when I finally get to the trip. So what's my expectation about, let's make sure we get the early part first. The early part is not so bad because I'm increasing my velocity due to the acceleration. What's the shape of that increase look like? What form does this plot have?
So it should be like linear?
It should be like linear, exactly, right. So in other words, it basically goes, there's some point that it goes to, but it basically goes in a perfectly straight line, like this, right? Because v is equal to v0, which is 0 plus at. So it's just going straight up linearly, okay? What does it do when it comes to the other side?
So it goes straight down.
It goes straight down, because again, it's 0, exactly. So right, so you notice there's a nice symmetric appearance here, right? And in fact, there's two completely acceptable ways to solve the problem. One is to do what I did in class on Tuesday, which is to break the problem into 2 completely different intervals and reset the clock. But a conceptually simpler way is to say the first half of the trip looks just like the second half of the trip, except for I've flipped it, right? Okay. So I can argue by symmetry that this half and this half have to be the same. Does that make sense?
Yeah.
All right.
Thank
you. And I won't do X, but here's the key thing. Does in this plot, the velocity goes up and then it goes down. Do I ever back up on this trip? Do I ever go backwards?
Nope.
Nope. So that means that whatever X does, it had always better be increasing for the whole trip. It never comes back down. Right?
I see.
So be careful with that. That's a common mistake is to go, oh, it's going up and then it goes down. No, that's not right. It doesn't go down. It keeps going up. It just doesn't go up as fast. Okay.
May I ask another question about
sure.
the problem 2? So,
sure.
So for the F part and G part.
Yep.
So we're looking for it. Let me check the problem. So we're looking for the velocity or the acceleration at that point.
We're trying to infer that.
Yeah, so we're looking for, we're trying to estimate the acceleration of the particle at time equals 3 seconds. So
yeah.
So since we know the function of velocity, so what I did was I used the y intercept, and then I would have 2 roots. So I find the function like using algebra, and then I used the
so I'm sorry,
take the derivative.
So you
do that?
Yeah, you can. You have to be clear. I mean, how do I say? I didn't give you the function. The function is just drawn on a piece of paper, right? So you don't have an analytic form of the function. Do you follow what I'm saying? Doesn't mean you can't turn it into an analytic form. You could argue, oh, it's linear here and it's parabolic here, and you could infer what the function looks like. But you have to tell me. You have to tell me how you did that.
So I can tell you like how I did that.
As long as you make it clear what you did. You can't just write the function down and say this is the function, because I don't know how you got that. But if you tell me, I measured some points and I fit that to if you just give me a description, that's fine too. Another thing that's perfectly fine is to say, the acceleration. What is it? So graphically, how does the acceleration? What is the acceleration? You say the acceleration corresponds to the derivative, right? So on a graph of the velocity versus time, how do I evaluate the derivative of it at a point? What does it graphically correspond to? Corresponds to a slope, right?
Because seems to me the graph is just like parabola.
It looks. I'm not saying that's wrong. I'm saying you can do that. But suppose I gave you a function where you have no idea what it is. Suppose it's doing this, okay? And I want to know what this. Suppose it's that. Suppose I give you this, and there's no way for you to fit a function. And I want to just say graphically. Show me graphically. This is velocity. Well, how would I get the acceleration at this point graphically?
So we need to find like a integral that we can.
Oh no, you're mixing up. To get the position, you got to do the integral. Yes. What about the acceleration?
Acceleration then. So we need like chop it into a chunk that.
Now you're making this problem too hard. I'm not asking for the position. I'm asking for the acceleration. What's the definition of acceleration? Tell me what the definition of acceleration is.
So that would be like derivative of velocity.
Yes, thank you. dv/dt. Graphically, if I want to calculate the derivative of a plot, what do I do? What do I
it's like the tangent line of.
Yeah, the tangent line, right. So a perfectly acceptable solution is for you to draw a tangent line on that plot and to measure the slope and measure the slope of that. That's perfectly acceptable too.
Okay. And then for the part G, we're looking for the position now. So for that part, we have to find the integral of the function.
Yes, exactly. So you got to do that integral.
So we need to find the velocity function first, then we take the integral of that. Is that?
You can do that. Again, you got to explain to me why the function is. But suppose I didn't know. Suppose I didn't have that. What would the integral correspond to?
So like
graphically, the area,
like
right?
Area.
Right. And so if this is a bunch of graph paper, how would I get the area?
Like Raymond's or something like that.
Yeah, so that's complicated and accurate. Suppose I want to do it quick and dirty. What would I do?
Quick and dirty?
Yeah, how would I? Suppose I wanted a quick estimate of the area under the curve. What could I do?
You take the integral, I mean.
Yeah, I know, but suppose I just give you a piece of paper and I say, tell me the area under the curve. What would you do? You're making it too hard, is what I'm telling you. Okay? Look, I got graph paper. What's the area of one square? I don't know, but I can calculate it easily, right? So I've got so what do? I've got all these squares. I basically, the area corresponds to the number of squares underneath the curve, right?
We just count the.
You just count the squares.
But that's not like accurate. I mean,
I don't. Read the problem carefully. I'm not asking you for an accurate answer. I'm asking you for an approximate answer.
So we're estimating it like literally estimating.
This is exactly. It is more important to me that you understand that the derivative is, and you can demonstrate your understanding that the derivative is the slope and the integral is the area, and that I can read these things directly from any plot, than it is that you show me that you're capable of figuring out what the function is and then analytically solving the derivative and the integral. But it's up to you. Either, as I say in there are multiple correct ways to solve the problem.
I see. Okay?
So your answer is perfectly acceptable, but it's harder than doing this. Okay.
But the important thing is we need to show that we understand that the integral of a velocity function is position, and then the derivative of the velocity is. Right.
Remember, the whole purpose of the homework is formative, not evaluative, which is to say, the whole purpose of it is to go to the exercise so that that you and I both agree, oh, this is how we approach it, right? This is the whole idea. And so as long as you make as long as these two ideas come through, and as long as you're showing me that you get these two things, that's all I care about. And how you do it for yourself. I'm not so, you can do Riemann sum, you could do Simpson rule, you could do all kinds of things, or you could just count the squares. And in fact, you'll see in my solution, if you're careful about how you count the squares, you can get very accurate. Like don't just count whole squares, you count you know, this is 0.5 squares, this is 0.3 squares. You can get pretty accurate. Okay. But anyway.
Okay. All right.
All right. That's
Thank
great.
you
That's
so
good.
much.
Oh, my
That's
pleasure.
all
That's
my
a good question.
questions.
That's a good question. Who
Thank
else
you.
has questions? Anybody?
Just making sure on part 5, when the ship turns around at the halfway point and starts slowing down, do you continue going to Sedna, or do you return to Earth then when it turns around?
No, you keep going. You have to say it's a one-way trip.
Okay.
So the turnaround. So here's so the way to think of it. So part of the goal of doing these kinematics problems is to imagine, is to have a technical description of the motion, but also to have in your head a conceptual movie for what's going on. And if you don't have it, it's easy to get. There's no way to sort of cross-check your answer. So the way to imagine this is the spaceship is, you know, parked in, you know, in near Earth orbit or something, and it begins to go forward, right? So you've got, you know, imagine a rocket ship. So here's my rocket ship, you know, with fins or whatever it is, and it's going, and it basically goes towards Sedna. So far, so good, right? And it gets to the halfway point. So if at the halfway point, I simply turned off the engines, I would keep going towards Sedna at coast, right? You with me? Mm-hmm. But instead of turning off the engines, what I do is I flip the switch, I flip the thing over, right? So I'm going this way. I'm still going this way, but now I'm thrusting the opposite way. So I'm slowing. I'm not reversing. I'm slowing down.
Okay.
That makes sense?
Yeah.
So in the problem, so in the problem, so this is the velocity. This is 0. I start off at 0 and my velocity increases. I'm going faster and faster, and then I turn around. Now I'm going slower and slower, but I'm still moving forward. I'm still going from Earth to Sedna. I never back up.
Okay.
Yeah. Any other? Oh, my pleasure. That's a great question. Anything else? Anybody else? I know you got a couple. I've got a couple lurkers. Well, you're either lurkers or you fell asleep during the main lecture and you haven't logged off yet. All right. So for those of you who are still there and you're still listening to me, I will be at the office hours at 4:30 today. And otherwise, if you have questions, just send me an email. I'm happy to answer them.